Hello, my name is Lior Saddam, design engineer, and I'm excited to present Mechatronics Lab 9, Frankenflower. The first goal of this project is to remotely gather weather data by utilizing various environmental sensors. The second goal of this project is to track the sun with a set of photoresistors and motors. The third goal of this project is aesthetic presence. To this end, the form was inspired by sunflowers and how they follow the sun to capture more light energy throughout the day. To get a better sense of what's going on, let's take a look at the processing output first. As you can see, the following metrics are taken. Temperature, pressure, and humidity from a BME280, light level from 3GL5506 photoresistors, UV index from an Adafruit 1918, dust and pollen count from a wave share dust sensor, gas concentration from an MQ135, and rain level from 2 high let go LM393s. For positioning, the flower utilizes an MPU 6050 accelerometer for altitude reading and a QMC5883L magnetometer for compass heading, aka azimuth. Scrolling and average lines have been added for trend visualization, while current and average text is output for precise reading. New data will overwrite old data in the array as shown on either side of the scan line. In extreme conditions, the processing script will notify the operator. High gas or dust concentrations will trigger icons to appear. High or low temperatures also trigger icons to appear. Depending on the light level, an animated sun or moon will play, and if the UV index is high enough, you guessed it, it will display yet another warning icon beside it. The base of the flower is designed to resemble a flower pot. The brains of the operation are stored here. An Arduino Mega acts as the controller, and I even added in subtle lighting. Acrylic sheets have been added for environmental protection, and small holes have been added for heat dissipation. For storage, transport, and protection, the flower occupies its retracted state, as seen at the beginning of this presentation. The extension mechanism is loosely based off standing desks. This version, however, is inverted, flipped, and designed for FDM printing exclusively. It was designed, modeled, and simulated by myself in SolidWorks, and printed on my Bamboo P1S, as are all parts in this construction. The extension mechanism allows the Frankenflower to extend up to around 2.5 times its height, around 5 foot total. It will extend to clear over obstacles for unobstructed viewing of the sky. Operating the extension is a NEMA-23 motor, driven by a DM556 driver. The altitude, azimuth, and flower motors are operated by a NEMA-17 dual shaft, single shaft, and mini respectively. These three are controlled by TMC2209 motor drivers. The admittedly awful stepper libraries in my code were written by me. It is coded so that the azimuth will wrap around if it rotates too many times, so the umbilical cable won't break, but it can continue tracking targets. To home the flower, the accelerometer and magnetometer are used for positioning feedback as it adjusts itself. To find the relative position of a light source, the analog outputs of three photoresistor voltage dividers are read and compared. The left and right resistors are compared for azimuth adjustment, then the left and right resistors are averaged and compared with the bottom resistor for altitude adjustment. I wrote the algorithm to adjust azimuth and altitude based on whichever has the largest difference to be accounted for. The magnitude of adjustment is based on the difference in light between the sensors, with sensitivity and threshold scaling in certain conditions to ensure proper performance. The barrier in the center ensures that each photoresistor can only gather light from a 120-degree span without gathering light from any other extraneous directions. Most of the sensors operate using integral squared communication, I2C, which is a method of data transfer that allows multiple devices occupying different memory addresses to communicate over two lines, SDA and SCL. This reduces the number of data lines needed. However, some sensors were only available in analog output, so some concessions of this had to be made. The LEDs are powered from the same power supply unit as the motors, so maximum instantaneous current draw must be closely controlled. In total, the steppers draw 6 amps, which is about the max current output of the PSU. The base stepper must be deactivated when operating the LEDs, and vice versa. The code accounts for this and disables the base stepper when not in use. Additionally, the PSU outputs 24 volts, so current limiting resistors must be used for the LEDs, alongside transistors acting as switches. The actuated petals have sensors mounted on them for readings. They also have acrylic sheets so that when the flower is closed, it will act as an umbrella to protect sensitive components. And finally, some other tidbits and notes. I spliced both rain sensors together so that it can take rain readings in both open and closed states with only one controller and one data line. I used an involute gear reduction for the altitude adjustment since the motor is not strong enough on its own, and to this end, bearings for friction reduction have been added. I'm using a capacitor on the PSU to avoid voltage spikes. Due to this, I can spin the motor shafts to generate back EMF and charge the capacitor, then subsequently briefly power the LEDs with the transient current, even if not connected to ground. And that's it. I hope you enjoyed learning about my project as much as I enjoyed creating it. Thank you very much for your time.